We're getting to the last portion of our program, and I'm really excited about this next presentation. As you've gathered here at Stanford, we are very interested in the future. We are very interested in having a hand in the future, and one of the big things that is looming in the future is quantum computing. Quantum computing in education is going to have a lot of interesting questions and possibilities. And here to present in 10 minutes all of quantum computing, we have Stanford's own Jelena Vuckovic. Please come on up, and if you can't get to all of quantum computing, at least tell us what a qubit is and why we should care.
Exactly. Thank you. Okay, thank you very much, Victor, for your kind introduction. And I think I may have even some extra time to answer any questions you have after I describe all of quantum computing to you in 8 minutes. But anyway, it's a great pleasure to be here. This is not the audience that I'm usually talking to. I'm from the Department of Electrical Engineering. I do research in quantum and in photonics. I also have 2 daughters in Palo Alto Public Schools, so I'm very interested in hearing discussions about education. And as a scientist and engineer, I care about teaching science, and there will be a connection between my talk and that. So the talk is about quantum computing in education, or quantum computing and education, and I'll tell you what I think about that, right? So you may have heard about quantum. It's a technology that people are talking about a lot together with AI. As you know, and it's discussed here, there are already a lot of interesting applications of AI in education. It's already there. Quantum is not there yet. It will, like AI, take decades to develop. And we should be ready, actually, when it's developed to learn it or to use it. So I'll tell you now where it is and what it could be useful for. So quantum computing is just one of the pillars of quantum technologies. There is also quantum sensing, quantum networking, quantum simulation. These technologies generally use similar platforms. There are some platforms that are more suitable for certain technologies relative to the other. But as I'll explain in a moment, we're pursuing all of them in parallel in the community. So what are these technologies doing? They're harnessing quantum mechanical properties of matter and usually light, or more broadly waves, in order to perform certain tasks much more efficiently. They're not a replacement for classical technologies. Quantum computers are not going to replace GPUs, AI hardware, classical computers, and likewise other quantum technologies are not going to replace classical technologies. They perform only certain tasks much more efficiently. So quantum computing, for example, provides great computational advantage for a certain number of tasks. Factoring of large numbers is one of those tasks, and factoring of large numbers is the basis for the modern cryptography, and there are a few other tasks, but quantum computer is not going to speed up PowerPoint or many other tasks that we're doing on classical computers. And as I already mentioned, we're pursuing several different platforms. People are working on superconducting quantum computers. That chandelier that you see in bottom left, basically just a fridge where you have a superconducting quantum processor. There is a lot of research on that at Google, IBM, and also in academia. In the middle, you see atomic physics-based quantum computer. And on the bottom right, you see semiconducting chips that I'm working on. Certain platforms are better for certain tasks. Semiconductors are, for example, the leading platform for quantum networking, which provides very secure communication. Some certain quantum sensors. At the moment, superconducting and atomic physics-based quantum computers are more skilled than others, but the race is still ongoing, and there is no clear winner yet. So that's really where we are. So what are quantum computers doing? As I said, they're all based on kind of harnessing quantum states of light and matter, or waves and matter, in order to perform certain tasks more efficiently. So for example, here you have atoms trapped in vacuum. Then you put some sort of mirrors around them. You have light trapped there. And then light interacts with matter. And matter is atoms and performs some quantum tasks. That's atomic physics platform. And then you may have heard about a material called silicon carbide. It's actually used to make fake diamond jewelry because it's cheaper than diamond and looks exactly like diamond. It's also used in abrasives. It's used in electric cars for power electronics. It's a semiconductor like silicon, but kind of has different applications. And recently, Meta announced Orion augmented reality glasses that attracted a lot of attention. And these augmented reality glasses that are in top right corner, they have lenses made out of silicon carbide. It's a material with high index. You know, when you go to optometrists, you can order high index lenses. So this is even a higher index than that, but it also has some interesting optical and electronic properties which allow people at Meta, for example, to structure them and make pretty much a really good computer in the footprint of glasses. So what I'm doing is using that material, silicon carbide, and also diamond to build quantum systems like the ones that people build with atoms. And this is how they look like. So that mushroom there is a real microscope image of a device that has diameter of about 10 micrometers. So it's smaller than human hair. It localizes light really well, like those large mirrors that you would put in vacuum. And our atoms are artificial atoms, which are just impurities inside of this mushroom. So you don't need to trap them. They're impurities that in high concentrations would lead to beautiful colors of jewelry, diamond or silicon carbide jewelry. We work with very sparse impurities because we want to individually control them with light or microwaves. And these impurities, which are kind of naturally trapped inside of this crystal, are what we call quantum bits, right? So they're different from classical bits 0 or 1 because they can be in superposition of some states. They can be superpositions of zeros and ones, and they can be used for quantum processing. So with this platform, people have already built state-of-the-art quantum networks for secure communications, some of state-of-the-art sensors. And again, it's either silicon carbide or its more expensive cousin, diamond. We work with both. But we also think that this platform is a very useful platform for building quantum computers and simulators going forward. And this is an example of how this works, right? So we're doing an experiment on it, driving it with light, with microwaves. And that movie on top right is an actual small-scale quantum simulator based on that mushroom of silicon carbide doing something that classically is already very difficult to simulate. So if you take a classical computer, it would be very difficult to really analyze everything that this is doing, but the system is actually doing some interesting physics. And having that said, for most of the quantum systems today, the main application really is studying different physical systems, right? So it's really pushing boundary frontiers of learning, frontiers of basic science. That's really what that movie on the previous slide is showing. And if you actually listen to announcements from Google or from IBM and they explain what they're doing and where they're gaining quantum advantage, is usually using the system to simulate another physical system. So we're learning a lot, but this is not yet broadly applicable as AI would be. The other important message here is that, of course, as these quantum machines become more complex, then new applications will arise. And I already mentioned factoring of large numbers, which is, of course, more broadly useful problem and task. But there are other problems that people are looking into, such as discovery of new chemicals, of new medicines, and so on. So there are applications beyond studies of other physical systems. It's also important to mention that some very small scale and proof of concept quantum computers are already accessible online at Amazon, Google, IBM. Students can actually access them and learn how to use them. And in fact, we're already using them for Stanford undergraduate classes and graduate classes. In order to get involved with that type of learning and using of these quantum machines, they do need to have a pretty solid background in math and physics. And this is really something that we can do now in order to prepare these new generations for using these machines as they become more complex. We need to teach them math and physics in K to 12 so that they're ready to basically get involved with these small-scale systems and quantum computers, and just also more broadly so that they can get involved with different aspects of science and engineering, not just quantum science and engineering. There are a lot of discussions about CHIPS Act, hardware manufacturing, semiconductors. I mentioned augmented reality. There will be a lot of jobs in the future, in the next few decades, for our students, and they need to get into the field early. They need to be ready. So at the very end, I'd like to just close by saying that I'm certainly not the only person doing this at Stanford. We have more than 60 faculty who are doing research in different areas of quantum science and engineering. We have Quantum Initiative, Stanford's like Quantum Initiative, which we call QFARM, which is an acronym for Quantum Fundamentals, Architectures, and Machines. And of course, you probably know that Stanford has a nickname, FARM, right? One important aspect of our work is education. Education is mostly focused on educating undergraduate and graduate students. We have a variety of classes from introductory undergraduate level, freshman level, all the way to advanced graduate level in the field. We also have fellowships for our students interested in doing research in quantum space. And many of these classes are also accessible online if you would like to see what is going on, right? And as I mentioned before, many of these classes also access real quantum computers online and teach students how to program them. We also have research, ongoing research in all of these areas. Our faculty are distributed across campus in sciences, in engineering, at SLAC, and there are more than 60 of them working on all of the different pillars of quantum technologies. And finally, we also have outreach, very active outreach, primarily through different seminars that we are organizing every week, workshops. We also support student clubs. In fact, Student Quantum Club is one of the largest clubs at Stanford, which tells you how much excitement there is about this technology. And QFARM supports that club, which is mostly undergraduate student run. And we have strong connections to industry through affiliates program, but of course, probably you know that there is also a lot of excitement about these technologies in industry. So that's what I wanted to say today, and actually I'm at the end of the time and happy to answer any questions you have. Thank you.